Okay, now let's talk about the depth first search. Already we have discussed the breadth first search, traversing technique to visit the nodes of a graph. We have discussed that in the BFS we have used the queue to implement. Now we will see that how the DFS can be implemented. This is the algorithm for DFS, depth first search. And if you look to the algorithms and the step of this algorithm, it is very similar to the BFS. The only difference is here we are using the stack in place of queue. Otherwise the steps looks very similar. So let us see these steps that how it can be implemented. So here we are using status variable. Already we know that there is one variable status that we are using in both the techniques, like DFS and BFS. Let me write here that DFS uses the stack. So here we use stack, and we are using one variable status whose value can be 1, 2 and 3. So initially all the vertex will be set as 1. So set status equals to 1, that is the vertex are ready to be processed for each node of the graph. Then we will push the starting node A on the stack. So the very first thing is we have to select one vertex as a starting vertex, and then we are going to insert it. We are going to push it. And whenever we are doing the push operation, so whenever you do the push operation, the status will change from 1 to 2. So from 1 it is going to change to 2. And the meaning is this is it's moved to the waiting state. And then we are doing this step 4 and 5 in a loop. We are doing these operation until the stack is empty, and when the stack is empty you have to stop. So pop the top of the node, and so we have to apply the pop operation. So whenever you apply the pop operation, so the pop operation makes the value of the status from 2 to 3. And whenever you apply the pop operation, you need to look to the neighbors, and then you have to push it into the stack. So here we are changing the status to 3, and then we are pushing all the neighbors into the stack, and when you are pushing them to the stack, their status will change to 2. So whenever you do the push operation, status will change to 2. Whenever you do pop operation, the status will change to 3. And whenever you do the pop operation, you need to do two things. One is change the status, and the second is push the neighbors. So these two things will be required every time. The key difference that you observe in the BFS and DFS. So in the BFS, when you are inserting the neighbors, so neighbors are actually inserted at the last, because we are working in the first in first out. So neighbor will be processed later. So first the nodes will be processed, and then their neighbors will be processed. But in the DFS, since we are using stack, so neighbors will be processed before the actual nodes, because we are doing the push operation, and whenever you apply the push, it will be taking a place uh, at the top. Okay, and the previous elements getting the position down, and the new elements will be stacked over to these old element. So this is the key difference that you can observe, that here whenever you find a new neighbors, they are keep on processing first, but in the BFS, the neighbors which have been identified will be added in the queue and will be processed at a later stage. So let us understand that how the entire things will work in one example. So this is an example, and this is the same graph I have taken, and we already discussed about this graph. Let us assume that these are the cities, and these arrow represent the flights are available. So these are the cities, A, B, C, D are the cities, and this arrow says that the flight is available from A to D. Already we have discussed the same example using the BFS. Now we'll see with the DFS. This is the agency list. This is how the computer will see the graph. So this is how it is stored, right? Now initially all the vertex will having the status equals to 1. This is the status value. We have to select one vertex as a starting vertex, and we have to push into the stack. So whenever you push, when you apply the push operation, that means you are changing the status to 2. In our case, we are assuming that we have to start from H. Now in our question, we want to check that how many cities we can go from H to different cities, means what different flights are available, so that we can reach to the different cities. Or you can see what are the different connections or routes are possible from H. This is what we are looking for. So here we are assuming that H is our starting vertex. We need to know our starting vertex, starting node, that we need to push into the stack. So initially when you start working on this, all are set to be 1. The status is 1, and when you push into the stack, the status changes to 2. So when you push H, it becomes 2. Now so you push this, and status becomes 2. Now you need to uh, pop this. So whenever you pop this, you will always change the status to 3, and you look to the neighbors. So the neighbors of H are E and I. So you are going to push this. You push E and I. Okay, and because this is a stack, then the topmost element will always be popped. So in the next stage, when you are going to pop, so you are going to pop I. So whenever you're going to pop I, the status of I is going to change to. Now keep in mind, whenever you are going to push anything, it will always be going to change the status. So in the previous stage we have pushed E and I, so the status of E is going to change to 2, and I is also going to change to 2. And in the next stage, when you pop I, means you will pop from the stack, and this is at the top element, so you're going to pop I. So I is going to change 3, and we are going two things. Whenever you are going to pop, you need to change the status, one thing, and you need to write, let me write here. So whenever you do the pop, first thing is change the status value, so status will change to 3. And the second thing we have to keep is, we have to push neighbors. So when you are going to pop this I, so you change this status to 3, and the neighbors of I is F. So you are going to push F, and since you are going to push F, so F is going to become 2 here. Okay, now you are going to uh, pop again. So every time you have to push, and then you have to look to the top element and then pop. And when you pop, you need to look to the neighbors and then push all the nodes. So here this is the topmost element. You will pop this. So when you pop F, so F is going to become 3, and you need to look to the neighbors C and H. So C is already 1. So all the nodes who are having status 1 are can be pushed only. So if any node is not having the status 1, you cannot work on that. So we have C and H. You are going to push this C, and H is not having the status 1, so we are not going to do anything. So you simply push C. So you can see C will be at the top element here. Now also you can see here we are keep on popping from the stack and printing here. So first we pop H, then we pop I, then we pop F. Now you're going to pop C. So whenever you're going to pop C, the status of C is going to become 3, and you need to look to the neighbors B and G. So you go to the B and G need to be pushed. And so B, when it's pushed into the stack, it becomes 2, and G is also going to be pushed. So the status becomes 2. So the next is we have already pushed B and G, so G need to be popped. When you pop here, we go to the neighbors F, H, and I, and we have already seen that F is already got the status 3, H is also got the status 3, and I is also got the status 3. So we are not going to push anything, and then so G is popped. So the next element that is on the top is B. So you are going to pop B. So when you pop B, you are going to set the status 3, and you will look to the E vertex, and E is also not having, already in the previous uh, working we have already set this E is not no more 1, because already we have processed this, right? So E is already having the status 2. It's already in the stack. So you can see here. is already in the stack. So whenever anything is in the stack, it is set to be in the waiting state and it's set to be 2. And when the status value is 2, you are not going to push it. So you simply pop it here, and then now this is your the last element. Then you are going, again you are going to apply the pop operation, and when you apply pop operation, you are going to change to 3, and you look to C and F, and C and F is already being changed from value 1, means they are not having value 1. So you simply pop this, and now the stack becomes empty. So when the stack becomes empty, that means you cannot move further, and these are all the possible nodes through which you can reach from H. So you can see here from H you can see I, F, C, G, B, E, and here you cannot see A. A is not visible here. That means in this given graph there is no possibility to move from F to A. Let us have a look here. Is it possible to move to A? So you can see that there is no possible path. Actually, if you look at A is or only having the outgoing edges, there is no incoming edges, so definitely we cannot reach to A. So with this DFS approach, we can find out that what are the different vertices are possible to reach from a given vertex. So this is how we can apply the algorithm to any real problem or to any real graph. So let us summarize. DFS is a traversing technique that is implemented using a stack data structure. It is using a variable status which holds three values 1, 2, and 3. 1 means all the nodes are ready to be processed. 2 means the nodes have been pushed into the stack, and 3 means it has already been popped and it has processed. So we can apply the DFS approach to find a path between the two specified nodes U and V in the unweighted graph, and also we can apply the same in the weighted graph as well. We can also find that whether the graph is connected or not. You can also find out which are the vertex are reachable from any given vertex. Already we have seen that from H what are the different vertex that can be reached, and we have find that vertex A cannot be reached. We can also find the spanning tree of the connected graph. A spanning tree means we are interested to make a tree out of the given graph such that all the vertex are included in that tree. So this is all about the DFS. So in the next lecture, we will take some more examples of graph, and we will apply the DFS and BFS approach and see how these algorithms can be used to traverse or to search a given node. That's all for this lecture. Thank you very much.